So hello and welcome to this hour lecture looking at materials transferring environment in nuclear materials, and a specialism in this mini lecture on space nuclear batteries or radioisotope thermoelectric generators. So I'm Dr. Sandy Knowles. I'm a UKRI Future Leaders Fellow and Associate Professor in Nuclear Materials at the University of Birmingham in the UK. So this area in space batteries, it's maybe a bit more speculative than some of the stuff, even more speculative than fusion, but there are quite a lot of efforts. We've had some of these things flying, so it is real, and there is initiatives to kind of have more interest in what we do in space with nuclear power, be that for power systems for a moon base or deep state space probes, or even thrust systems for getting to Mars. So there's quite an exciting area to be getting into, and there's increasing amounts of research going on. So thanks again to Arua for the invitation to give this lecture series, and also to GCRF and UKRI for supporting this initiative.
So we've talked around some of kind of there's many applications of nuclear around different industries. We particularly focused on power generation and then looking at next generation fission and fusion technologies. And today we're really going to talk around space and nuclear batteries of plutonium and curium. So why do we want nuclear power in space? So it's been kind of multiple kind of recent examples of nuclear power being employed. So in Cassini, in Curiosity and Perseverance. Then gradually going into the kind of sci-fi, we've got the Martian and the radioisotope thermoelectric generators used there, used to just heat the buggy in that movie. And then also now there's been interesting things, talking around, there was a recent announcement in the news from the UK Space Agency and Rolls-Royce, which are doing a study into nuclear-powered space exploration. So when we kind of see what SpaceX is doing in terms of getting out of Earth orbit, if we want to go interplanetary, maybe we want to use nuclear power to get there. And the key driver for all of these applications is when you're in near Earth orbit, you can probably often rely on solar energy, and that can be quite reliable. But depending on where you want to go in space, you're not always going to be close to the sun, so you won't be able to rely on solar panels as your primary energy source. So as you particularly go into deep space, the real advantage of nuclear is a long-term, reliable, it's not dependent on environmental factors in terms of being able to see the sun, that you can have these long-term power generation. And so that's what we're going to be talking about in this lecture, is these radioisotope thermoelectric generators. And so we'll kind of be talking through in a bit more detail this kind of figure on the right from NASA. So this is using plutonium-238 as our heat source, and we'll go into a bit more detail on that. We're then using thermoelectrics to convert the heat from the decay of radioactive material, which generates heat, and to convert that heat into electricity. And also we've got a lot of then sophistication in the structural materials employed, and I'm biased because structural materials is my main research area, so I'll probably spend more time talking about that. It's not the only geometry, so this is one method of using nuclear energy to create power in space. This one's relatively modest energy, so thermal load and modest energy generation. Particularly say that initiative between UK Space Agency, if we want to do it for propulsion, there's nuclear electric thrusters and nuclear thermal thrusters, which are different technologies, but also probably quite interesting to look up to if you like this sort of stuff. So what is the kind of key thing that's going on here? So we're first going to talk around the kind of the heat source itself. So there's plutonium-238. So the nice thing about plutonium-238, it's going to decay into uranium. It's going to release helium and quite a lot of energy. So we have this kind of alpha particle released. So one thing is that half-life for this reaction, it's reasonably long but reasonably short. So in that sense, there's a kind of bit of a balance here. If it was very short, then it would decay very, very quickly, and that doesn't give you energy for a very long time. So there's a bit of a balancing act for how long you have energy for if you have a very long half-life, but also how intense it is. So the faster it's decaying, the more energy is being released over a given time. So this one, plutonium, is quite a nice balance, because if you imagine, okay, well, a reactor, a power plant in space, an experiment that might last a decade or two, the power output of the plutonium and the decay rate and the power output is not going to change too significantly. So you can imagine that after 87.7 years, its power output, there's half of it there, therefore its power output is halved. So you can then kind of back calculate what that means in terms of, say, the Voyager and things like that, which have been around for kind of decades. They're just gradually losing power. But they are still getting decades worth of power, which is completely different to, say, other isotopes we might select. So plutonium is quite effective there. So as mentioned, we get this decay into uranium and then an alpha particle, which also gives us energy. So we're getting this energy out, so again, our E equals mc squared, which is going to be our heat generation. One of the quite convenient things about this nuclear reaction is that the alpha particle are quite easy to shield. So if we looked at different decay pathways or different isotope decays, we might instead be having beta or neutron involved in the decay, which then are much harder to shield. So actually this is quite beneficial in terms of how complicated it is to build our generator and the entire component geometry, that we don't need that much shielding material compared to what we might need for other reactions. One of the things that's kind of quite curious is, where do we get all this plutonium-238? And all of it really is being created as the byproduct of plutonium-239 that was created for enrichment programs and isotope selection for nuclear weapons production. But this has meant that, especially in the US, NASA has had a great amount of access to plutonium-238 that is effectively just a waste product from the military perspective. So plutonium-239 is not suitable for space applications. It's got much too long a half-life. But this kind of leads in from NASA's perspective, a kind of slightly curious sort of situation where we have sort of multiple kilogram quantities of plutonium-238, but it's quite a finite supply. And there definitely is an eye to the horizon that we don't have a guaranteed supply pathway for plutonium-238 as we do experiments into the future. So for the next decades, we're probably okay. But as we go to kind of 20, 30, 40 years, probably we're going to have to consider either creating some more plutonium-238 or looking at alternative isotopes. And there might also be other benefits in looking for alternatives. So depending on the half-life we choose, we either could make the power pack last for longer, or alternatively we could choose decay pathways which release more energy. So it depends whether we want more energy or more lifetime. I also found it just kind of, in finding out more about this, then there's a quite interesting little story around Albert Stevens, which in 1945, at a time when there weren't ethics studies, he was injected with 131 kilobecquerels of plutonium, which then was within his body and stayed within his body, which is given and a continuous dose over time of these kind of helium alpha particles, which has meant that of records, he's the highest ever recorded dose of radiation. And when we kind of have these concerns around kind of nuclear energy and radiation and concerns around safety, Albert Stevens lived to 78 and did not die of directly a radiation-based disease. So it's a kind of interesting thing that even in someone who's had the highest ever known recorded dose, they weren't so severely affected. And so there's a very interesting thoughts around what we perceive of radiation and radiation dose. But I wouldn't want to do that. So in terms of, this is a lot of work from NASA. So they have what they call the general purpose heat source module. So we've got a plutonium dioxide as the fuel. So again, in the same analog compared to in fission where we use uranium oxide, the oxides are much more stable than the pure metal. So in terms of temperature stability, and it can't burn. We then have an iridium cladding, which is just something that's very soft, ductile, and temperature capable. So plutonium is there as the heat source. The iridium is a barrier to make sure that the plutonium stays where it is. It's got a high melting point. It's also very resistant to oxidation or also to interstitial. So it's going to stay ductile even after being contaminated with interstitials. And the next parts of this assembly are mostly structure. So to kind of hold everything in the right place. And these are graphite or carbon fiber composites, so critical design names there, that they're very lightweight, They also have good heat transfer properties. And also in this application, one of the concerns is if this thing does land, that's obviously going to have quite an impact event, even though we try to minimize that as much as possible with parachutes and thrusters, etc. But there still might be a possibility of that impact, and these can help absorb that impact to mean that the fuel, you don't want a spacecraft going to crash and the fuel to be distributed over the landing zone. So both the iridium and this carbon and graphite structure are to make sure that the fuel would stay integral. It wouldn't be scattered across the environment in an accident or an impact. So the next part, so we've got that kind of heat source generation. The next part is this thermoelectric materials. So we kind of often are seeing kind of resistive heating, the conversion of electricity to heat. That's kind of almost our waste byproduct in many applications, or we might use it for heating. So for example, in space applications, then you're often wanting to heat components to make sure that they are kept warm enough. So that's sometimes where you're having to use energy. But if you want to convert heat to electricity, that's a little bit more tricky. It's not something which all materials would do. Well, the interesting thing is that all materials do it, which is there is a thermoelectric or Seebeck effect. But the criticality is that mostly it's just so small to be almost insignificant. And it's actually quite specific materials that have a very high Seebeck effect. So bismuth telluride is one example, where you have this kind of combination of high electrical conductivity but low thermal conductivity, and this net effect that you get a high Seebeck coefficient. And so all of these give you something which then we define as a thermoelectric material, where the thermoelectric effect is significant. And so ultimately what that means is that if you apply a temperature difference across the material, you'll get a thermoelectric voltage in response. So one example might be thermocouples, and as we'll talk about in the thermoelectric generators here. So a lot of this comes down to the complexity of the crystal structure. So if you went kind of delve deep into sort of condensed matter physics, this is kind of some of the theories that we kind of spend more time on. In terms of the radioisotope thermoelectric generator and RTGs, then the materials we use, we really need reliability. We need long lasting. Something that's kind of interesting to know is that the efficiencies are quite low on these things, so only about 3 to 7%. So the conversion of heat to electricity. So we use things like silicon germanium alloys, lead tellurides, antimony and germanium, so relatively exotic, often toxic material. So cobalt arsenic is then another example. And silicon germanium, which is then probably one of the ones which has been most widely used in RTGs. So some of this situation, then we all again have these kind of anisotropic crystal structures, which give this kind of difference in thermal electrical conductivity compared to thermal conductivity. And actually, in order to kind of join that into a thermoelectric generator, we do have a hot plate on one side and a cold plate on the other, so we have our temperature difference. And then we do what's called N-doping and P-doping. So this is it's a band gap or electronic structure theory. So maybe some people might go back to that in a more physics direction, so kind of almost applied quantum mechanics. And if we do that, we have this kind of difference in temperature and create an electrical circuit between two of these thermoelements with different, obviously, insulators, electrical conductions, and heat and cold. Then we can use that to generate electricity. And so that's kind of the basis point of how we get to this RTG. If we didn't have the heat source, we didn't have the thermoelectric, we don't have an RTG. So this is then more kind of my core research areas around kind of then structural materials that we're going to employ. So these things can get quite hot. The hotter we go, the more extraction efficiency we could potentially gain. So we've got high temperatures, we've got irradiation damage, so we need to be resistant to that. We want the heat in certain places, and we want to avoid the heat in others, so we either need conductivity or insulative, and equally true for electrical conductivity as well. And also we might need some kind of shielding. So depending on the electronics, then we don't want this alpha particles from the nuclear reaction or alternative nuclear reactions, so neutrons or beta particles, to damage the electronics in the actual spacecraft. So there's also a slight shielding component, but luckily with plutonium that's not too severe. So what are the kind of materials we use? So we kind of start off with some of the nickel alloys. So there's Haynes 25. So this is the nickel cobalt alloy, so an FCC structured material. So actually this one's cobalt majority. Some of the other Haynes alloys are nickel majority. And this we've got a kind of combination of high temperature strength, so up to 980 degrees C. So that is partly based off the high melting point of cobalt and nickel. And also the FCC crystal structure that also has kind of quite slow diffusion kinetics. The other element of Haynes 25 is that it's got very high chromium content, and so this provides us oxidation resistance. So we have high temperature strength and oxidation resistance nearly to 1000 degrees C. So you can see there's quite a few different points in the RTG where Haynes 25 and other nickel and cobalt alloys are used. The next one then is looking at aluminium alloys. So here one of the advantages of aluminium is it's got very high thermal conductivity. So there's also obviously very high electrical conductivity as well compared to many materials. But in this case the thermal one is one advantage. And particularly that we can form it to shape, we can make these cooling fins, and they are quite low density. So your alternative might be for thermal conductivity might be copper, but copper's much denser. So aluminium wins out here. In terms of electrical and thermal conductivity, often there's an interplay between copper and aluminium. It's often traded off for one another. Also an advantage in this application would be the formability of aluminium. It's quite got moderate strength, so it's sufficient for the application, particularly quite good specific strength because of that low density. It's not going too hot, but it does have oxidation resistance. We don't have to worry too much in this application about it corroding. But it's more limited in its temperature capability. Aluminium is melting not much above 600 or 700, so you don't really want to be operating it above 300. So that limits the locations where you might use it, and means that you exchange for things like cobalt and nickel for higher temperatures. Then got a fair amount of usage of stainless steel, so highly machinable and formable and joinable. One advantage. It's strong, it's oxidation resistant, and it's got pretty fair temperature capability and a fair bit cheaper also than say Haynes 25. But in this application you're not too bothered about cost, it's more just what's the best material for the job. Quite nice in that kind of space applications, it's just ultimate performance gain. And then we've got kind of closer into kind of my patch, so I spend a lot of my work doing BCC based materials, so particularly if we wanted to go further higher in temperature, we really would even max out. We wouldn't be able to use stainless steels, we wouldn't be able to use potentially even the nickel alloys if we went to very high temperature reactions. Another advantage in terms of the BCC elements, so particularly refractory metals, for example tantalum, is also the irradiation damage tolerance. So actually in terms of damage tolerance and irradiation-induced defects and irradiation-induced helium, nickel and cobalt don't do well in this regard. So in terms of irradiation damage, BCC is generally advantageous. Tantalum has very, very high melting points, so about close to 3,000 degrees. It's quite corrosion resistant, but it's potentially bad for oxidation resistance. So actually, one of the projects we have going on at the moment is oxidation resistant refractory metal alloys. So trying to find this balance of properties and do we get a better overall performance. So in this case we just use quite close to tantalum or minor alloy conditions, and we're looking at can we develop new alloys in that regard. So I think that's then where we wrap up in terms of structural materials. So we've kind of gone through and talked a bit around the heat source itself, the thermoelectric generators, and the structural materials. So you've got the different demands in each application. Each of those components has a different demand and expectation on it. And that then changes and defines what materials you might select for that end application, depending on the balance of properties needed. So I hope it's been interesting kind of to learn a bit around this material selection and design for nuclear space applications and for the other nuclear applications we've been talking about in the previous lectures. So thank you for listening.